Welcome to this talk. Today, I'm very excited to share this new project on autonomous vehicle market design. My name is Jen. I'm a fifth-year PhD student at Cornell Johnson and Cornell Tech. This is a joint work with my advisor, Gert van Rijzen. Autonomous vehicle is a super cool new technology. Except for just being cool, there are also lots of benefits people expect AVs to bring. Since there's no driver, every passenger can work in their commute. AVs are also thought to be safer than human driver, although there's kind of some debate around this after a few accidents. But people also hope that this new technology can improve the whole transportation ecosystem, for example, by help solving the congestion problem. But the most important reason the firms invest heavily in AVs is the lower transportation cost for AVs by replacing human labor. For the ride-hailing platforms, AVs are a particularly important strategic move. The current ride-hailing market is valued at $100 billion level. Out of that $100 billion, the cost of human labor is more than 50% of it. So you can get a rough idea about what kind of cost savings AVs are expected to bring. For automakers, AVs are both an opportunity as well as a challenge. One common vision for AVs is that in the future, private car ownership will just not exist. You will just order a ride on an app, AVs come pick you up, drop you off, and then keep running on road, picking up someone else. If no one buys their own car, the auto business is going to be completely different. That is why automakers want to be the first one to invent the AV technology and gain some first mover advantage. For some even more ambitious automakers, they don't just want to build a car, but also want to expand business to have their own ride-hailing platforms and get their share of this billion-dollar business. That is why, even if the technology is not mature, we are already seeing many firms exploring different business models for AVs. We have ride-hailing platforms building their own AV fleet. For example, Uber has this department that is dedicated for developing AV technology. There's also ride-hailing platforms collaborating with AV companies, for example, like this partnership between Aptiv and Lyft. They jointly fulfilled over 100K paid rides in Las Vegas as of February 11th this year. There's also this more ambitious strategy for AV companies, like GM Cruise, are developing their own ride-hailing service. Another important player is Alphabet's Waymo. Waymo is kind of trying two things at the same time. They have the partnership with Lyft, but they are also developing their own ride-hailing service. So how does this affect consumers? It is a widely believed opinion that AVs will bring lower prices. The logic is that AVs do not require human drivers to operate, so eliminate that human driver cost. And lower cost is going to lead to lower prices. Well, this is a great promise, but we don't know whether this is true. There's substantial difference between AVs and the existing human driver market. In order to fully understand the social impact of AVs, we need to first get an understanding of its economic model. This is the main thing we want to look at in this project. We want to see whether the market design for AVs are going to affect these potential benefits. In particular, we want to explore these two dimensions of market design, the platform configuration and the level of competition. For platform configuration, we look at two scenarios, basically whether or not to let human drivers and AVs operate on the same platform. As for the level of competition, we consider the two extreme cases, the monopoly case and the perfect competition case. Overall, if we are going to show that the market design of AVs will indeed make a huge difference on the AV's potential benefit, then this is actually a super strong conclusion. It means for policymakers, in order to achieve those welfare benefit for AVs, they need to pay attention to these two things. A little bit about the literature. So right now, there's not many papers that focus on the economic analysis of AVs. Here, in the interest of time, I'll just talk about these two that are most relevant to our paper. This paper by Michael Ostrovsky and Michael Schwartz discusses the relationship between carpooling, road pricing, and a pure AV supply. Our paper is different in the sense that we consider both human drivers and AVs, but we do not consider carpooling. The second paper by Owen Siddick and Terry Tiller discusses how the access to AVs would affect the competition between two ride-hailing platforms. In our case, we do not consider the competition between the ride-hailing platforms, but instead focus on the market design when you consider both human drivers and AVs. So I'll switch gears to the model setup. There's two types of supply, the AVs and the human drivers. Our assumption for human drivers is that human drivers have abundant supply and the market is perfectly elastic. We assume that there is a fixed outside wage for human drivers. You can think of it as the sum of the operating cost for the human driver's vehicle and the driver's reservation wage. The human driver's fixed cost is zero because in ride sharing, the most popular model is that human drivers already own the car and they only use this car for ride sharing to earn some extra money. So they did not purchase that vehicle specifically for doing ride sharing. We assume that the supply of human drivers is perfectly elastic. This means that if the earning per hour for human drivers exceeds the outside wage, W0, then an unlimited number of human drivers would want to participate. And if the earning per hour is less than this outside wage, W0, then no one will want to participate. The result is that there is a zero profit equilibrium for the human drivers. Because otherwise, as long as the profit is positive, more drivers will enter the market unless the profit is driven down to zero again. Our last assumption for the human drivers is that the labor market is loose. This is the most realistic setting for ride-hailing platforms. In other words, this means that a pure human driver market is viable. So this is the human driver market we focus on. For AVs, our first assumption is that AVs are fully functional and can serve the same types of trips as human drivers. This is obviously a not very realistic assumption because right now, AVs still have many limits and can only serve rides on certain types of roads. But our analysis won't be affected. All the conclusions will go through by only considering those areas that AVs are able to serve. The most important assumption for AV is that AVs has a cost advantage over human drivers. So what does this mean? There are two parts for AV's cost. There's a variable cost, which can be thought as the operating cost of the vehicle. There's also a fixed cost, which is the purchasing cost of AV divided by its lifetime. So this is the cost the AV owner is going to incur regardless of how much he used the AV. And AV is cheaper than human drivers in the sense that the sum of this variable cost and the fixed cost is lower than human drivers' outside wage, W0. Another thing that is different from human drivers is that the capacity of AVs is assumed to be pre-committed to the market. So in other words, the AV fleet size will be constant once the decision is made. The consideration for this assumption is that the decision horizon for AV capacity is much longer than for human drivers. For human drivers, the capacity is almost immediate, it's almost instant. But for AVs, there's a planning horizon for that. So in the time frame of our consideration, we assume the AV fleet size stay constant once it is determined. So that's for the supply side. In terms of the market, we consider stochastic aggregate demand. There are a couple of different demand scenarios which you can think of as the different hour in a day. For each demand scenarios, there's a certain probability of that scenario to happen. We assume that the product market is competitive. So human drivers and AVs, they provide the same service and charge the same price. They compete on the quantity, and the market level price is determined by the total supply of human drivers and AVs. The last piece of the model that I want to highlight is this platform density effect. Our model endogenously incorporates this platform density effect by assuming that there are 3 states for the supplying vehicle. A vehicle can either be waiting for dispatch, or picking up riders, or fulfilling the demand. Among these 3 states, only the third one, fulfilling the demand, is profit generating for the firm. So as the supply and demand density goes higher, the average density between a rider and a car becomes shorter, which means the vehicle can spend less time picking up riders and spending a higher proportion of time fulfilling the demand, which means they have higher utilization and becomes more efficiency. So this effect of higher density leads to higher utilization is the platform density effect we're talking about here. And this is going to be essential in driving our main results. So given the market conditions and supply and demand assumptions we just discussed, next we move forward to talk about the AV market design. As we've discussed at the beginning, there are 2 considerations: the platform configuration and the level of competition. The first one is the common platform market design. So in this case, human drivers and AVs, they share the same dispatch network and the same rider pool. This models the situation when a ride-hailing platform has its own AV fleet, just like if Uber has its own AV fleet, or there's partnership between a ride-hailing platform and an AV platform, AV company, sorry. So which is basically the case between Lyft and Aptiv. The other possibility is that human drivers and AVs, they operate separately. There are separate groups of drivers who use the AV platform and human driver platforms. This is the case when an AV company launches its own commercial ride-hailing service and competing with a human driver platform. The level of competition is the second consideration for the market design. We start with the monopoly case. In this case, we assume that a single firm has a 2-stage decision process. The firm first selects an AV fleet size, which is the capacity. And in the second stage, subject to the capacity constraint, the firm decides on the supply level it's going to use based on the demand scenario I in order to maximize its profit. The other extreme of competition we look at is the perfect competition. In this case, multiple firms have access to AVs and they make their own decisions about the fleet size and when or whether to operate AVs in a certain demand scenario. In reality, for example, Lyft has this open platform which allows multiple AV firms to operate. Perhaps something more similar to the perfect competition case is Elon Musk's vision for Tesla. So each Tesla owner in the future can decide to put their vehicle on road and let their vehicles to do ride sharing when they're not using it. In this case, there's also a 2-stage decision. First, decide on whether to purchase an AV based on whether the expected profit is greater than the unit cost. And conditional on purchasing, the AV owner decides on whether to operate service in a given demand scenario. Combining these two dimensions, we have these 4 cases in total. Our goal here is to compare these different market designs with the pure human driver market to see how the introduction of AVs going to affect the market outcomes like prices and coverage of services. We also want to look at how different market designs are going to affect this comparison. In the interest of time, I'll not provide any technical details, which will be in the paper, but I'll just show the high-level managerial insights. Our first result is simple, but it's very important. It says that even if AVs are cheaper than human drivers, under most conditions, they will not fully replace AVs. The driving force is the demand uncertainty. It is true that if there's only one demand scenario, then AVs are always cheaper than human drivers, and it is strictly better to use AVs to supply the demand. However, as long as there's demand uncertainty, this no longer holds. The intuition is that although AVs are cheaper per hour, even if you count both the fixed cost and the variable cost, they still require a significant capital investment. So for any firm to hold large numbers of AVs but not to utilize it much, this is a very costly decision. It's not economical to acquire a large number of AVs but not to utilize it. As a result, in most of the equilibrium, the AV capacity in equilibrium that maximize the monopoly firm's profit or satisfy a single owner's profit maximization would lead to a capacity that is lower than the peak demand. In other words, in equilibrium, the AV capacity would not be enough to satisfy all the demand from all the demand scenarios. The residual demand can then be satisfied by the human driver. An analog of this would be the electrical power market, which also has a mixed production technologies with different cost structure. Although nuclear power is cheaper than gas, the gas is not replaced. Gas is still used to serve the peak demand. In this sense, AVs are cheaper, but it does not fully replace human drivers. It is better to use AVs as a baseload technology and using human drivers to satisfy the peak load demand. The second result is a really surprising one. We found that the only market design that leads to unambiguously lower prices is a perfectly competitive common platform market. In other words, to achieve the social welfare benefits from AVs, we need to get 2 things both correct. We need to ensure that AVs and human drivers are operating on the same platform and are integrated. We also need to ensure that the AV operators are competing with each other. We also found that in the worst case, if AVs and human drivers are designed to operate on separate platforms and the AV operator is a monopoly, introducing AVs actually lead to higher prices in all demand scenarios compared to the pure human driver market. This highlights the importance of market design. So as a summary, we found that even if AVs are cheaper, there's still a market for human drivers. We found that AVs do not necessarily lead to lower prices, and the price is only uniformly lower in a perfectly competitive common platform market. Combining everything together, this tells us platform configuration and the level of competition are both essential in unlocking the economic benefit of AVs.